Okay, this is step two, 2015, question one. Um, Quite an interesting question. Yeah, for sure. Yeah, for question one, it isn't super easy, and from the examiner report, which I will show later, it seemed as if a fair amount of people struggled with the question, even though it was a popular one. So yeah, let's just get into it. So f of x equals x minus natural log 1 plus x. It's just good to define it to begin with. And we want to show that it's positive for all positive values of x, which essentially means we just want to show that the function is positive for x greater than 0. Okay, so it's good whenever we think of a function being positive, we just want all of the points to kind of look like something like this, right? Just essentially all be above the x-axis. Now, a good way to prove this is first evaluate the case of when x equals 0, right? So f of 0 just equals 0 in this case because it's just 0 minus natural log of 1, which is 0 in itself. Um, so we have a point at the origin. So if the function is increasing from the origin onwards, then the f of x, which is x minus natural log 1 plus x in this case, is greater than 0. Because if it's increasing, that means from the origin, it's just it's getting bigger and bigger. Like the values of f of x are getting bigger and bigger as the value of x is getting bigger. So therefore, it can't be negative, right? So it has to be positive. So now that we've evaluated that f of 0 is 0, we just need to show that the function is increasing in between our domain or in our domain. So f dash of x here is just equal to 1 minus 1 over 1 plus x, which when you expand it and stuff, it becomes x over 1 plus x. Now, obviously, this for when x is greater than 0, this is greater than 0, so our function is increasing uh, from the origin, and therefore f of x will be increasing. So in conclusion will be, since f of 0 equals 0 and f of x is greater than 0 for x bigger than 0 or equal to 0. Oh, sorry, no, from x greater than 0, then f of x is greater than 0 for all x greater than 0. Cool. Pretty chill way to start the question. Now we're going to use this result to show that we can obtain this. Now, from part one, or well, from the stem part of part one, we showed that this is true. This is true. Now we can do some rearranging and we get this. Now this is we've now gone the inequality in kind of the same direction as what we want to show, but it's not the same, right? Because we've got a k and we've got an n and we've got a summation. Now we've got to think, right? We can let's first think about the k value, right? Why don't we try a substitution? We can try let x equal 1 over k, and this is just something I want to try because it's step, right? You have so much time, so you can just try tons of different things. And this is one of the things I want to try, just because we're kind of, I think the hint for this is that our inequality is in the same direction, so we might as well just try the substitution. So we get 1 over k is greater than the natural log of 1 plus 1 over k. So 1 over k is greater than the natural log of k plus 1 over k. Right. Now what we can do is we can take the summation of both sides. Now this is kind of it's probably a bit weird to hear, right? But essentially, let's say we had two functions, g of x and f of x, right? Or g of x is bigger than f of x. It's not for us, it doesn't, or like for most people, it doesn't feel weird to take the integral of both sides, right? We can take the integral of both sides, and no one would really bat an eye, or not really bat an eye, but no one would really, think this is a weird thing to do. But essentially, an integral is just a summation, but a very accurate summation, right? With very thin strips. So we can do the same thing here. It's the same sort of concept that's being applied, provided that your limits for the summation are the same on both sides. We can just do this. Sorry, that was a horrible summation sign. Let me just get rid of that. Now using log laws, what we can just do is just do this. Now, what we have here is we've kind of just brought ourselves to a method of differences, right? Because we have two functions being subtracted. So best thing you can do here, and even if you don't know what method of differences are, it's still a very accessible question just because you just sub in values of k, right? You could literally just sub in k is 0, k is 1, k is 2, k is 3, and just kind of pray the sum converges to a value. So let's try it. So we get natural log 2 minus natural log 1, natural log 3 minus natural log 2, natural log 4 minus natural log 3. Now I'm guessing you can already see kind of what's happening, right? Natural log 3 will cancel, natural log 2 will cancel. Eventually natural log 4 will also cancel. And if you keep going down, the only term you'll be left with is natural log n plus 1 minus natural log n, but natural log n will cancel with the one before that, so you'll be left with these two terms. But we know that the natural log of 1 is just 0, so we end up with this whole summation being just equal to natural log n plus 1, so we just can show that result, we get that result, which is what we want. Nice, perfect. Pretty not too hard, but I think the main difficulty is just spotting those substitutions and realizing you can take a summation of both sides, because I think it is if you told someone usually, oh yeah, I'm just gonna take the summation of both sides, it just sounds a bit weird, at least from a further maths or like just a normal maths standpoint. But yeah, pretty chill, not too bad. Part 2 is a bit harder though, or considerably harder, but still very accessible, I think. Let's get rid of that. Although I will admit this question did, at least part 2 took me a lot longer than it should have, because genuinely just because of this one definitely ruined me, for sure, and the limits of the summation, which I'll get into in just a second. I'm gonna get rid of all of this just so we have just so it doesn't get too crowded. I don't want to go into like a different page. So cool. Now we want to consider this function, right? So now call it g of x is equal to x plus natural log 1 minus x. Okay. Very, very, very important we pay attention to the function inside the natural log. Now we know that natural logs can only be defined for positive values. So that means our domain has to be between 0 and 1. Well, not even between 0 and 1. It has to be less than or equal to, greater than or equal to 0 and less than 1. So this is our new domain, okay? Anything past 1 is just undefined, or equal to 1 is undefined as 2. So now we do the same thing, right? We evaluate g of 0, which also becomes 0, because again, 0 plus natural log 1, which is just 0, is 0 plus 0, which is 0. So now we just need to see if the function is decreasing or increasing from this point. So we do g dash of x, which is 1 minus 1 over, 1 minus 1 over 1 minus x, which becomes minus x over 1 minus x. Now for the domain of 0, of greater than 0 and less than 1, this is a negative value. This is actually just all negative. So basically this is less than 0. So that suggests our function is decreasing from the origin onwards. From the origin onwards. And if it's decreasing from the origin onwards, then we could say that this function in itself is always negative. So f of x is less than 0 for all x. We don't really need to write a conclusion because it's not telling us to show this, but it is probably necessary for this question because we need to set up an inequality, right? So now using this result, right, we can say x plus natural log 1 minus x is less than 0. So x minus x is less than minus the natural log of 1 minus x. So x is less than natural log 1 over 1 minus x. Just doing the log laws and stuff, right? Now, it's a bit different because we have an upper bound of infinity for our summation, and we also have a 1 over k squared. Now let's tackle the kind of the change of variable first, right? So let's do a substitution of x equals 1 over k squared. And again, I'm doing this because our inequality is in the right direction. And if this is wrong, we can change it because once again, it is step, and we can if it goes wrong, we can always redo the question, and we have ample time. That's the good thing about this paper. Time will not usually be an issue. So take the summation. No, not yet. Sorry. The reason I'm not going to take the summation from 1 to infinity is because first let's sub it in. I'll show you what's going to happen. We're going to get something like this: k squared over k squared minus 1. I'm not, if you plug in 1 over k squared into x and you simplify it, you get this. So what you realize is the reason I'm not going to do it from k is 1 to n is because when k is 1, this here is undefined, right? This is an undefined value. So we're actually going to do it from k is 2, since that's the next integer that works, right? Because, again, logs also need to be positive. So I'm going to take the summation from k equals 2 to n, to infinity, of 1 over k squared is less than the summation of k equals 2 to infinity of the natural log of k squared minus natural log k squared minus 1. Now we can simplify this further into the summation from k is equal to 2 to infinity of 2 natural log k minus I'm going to split this up into its difference of 2 squares. So minus natural log k plus 1 minus natural log k minus 1. Yeah, right, now all we need to do is just kind of sub in our values. So we get 2 natural log 2 minus natural log 3 minus natural log 2, 2 natural log 3 minus natural log 4 minus natural log 3, 2 natural log 4 minus natural log 5 minus natural log 4, 2 natural log 5 minus natural log 6 minus natural log. Sorry, this should be 1, 2, 3, 4. Okay. So what you realize is this, and this cancel, this, and this cancel, and eventually this, and something else will cancel. But pretty much all values except this, and this cancel, because this is going to infinity. This is pretty much going forever. So everything will cancel except these values here. So this will just equal the natural log of 2, because the natural log of 1 is 0. So it just becomes natural log 2, because it's 2 natural log 2 minus natural log 2, which is natural log 2. Right? So we have k equals 2 to infinity of 1 over k squared is less than natural log 2. Now, when we're missing a 1, right? We need the 1 here. And this is a big clue. In fact, this is why when I was doing this question, this is where I kind of got stuck, was because I was figuring out how to get the 1. But I realized, right, you get it from here. You get it from the left-hand side. And because when I was doing this question, I was starting from k equals 1 and going up to infinity. And the problem with that is that, like I said, you have an undefined value. So you get like infinities and negative infinities, and it just doesn't work out very well. But from here, but then I realized, it's undefined, so I should probably start the next integer up and kind of try that. And I realized that would work because the 1 would then come from the left. So I'll show you, right? So the summation of, what's happened? The summation of k is equal to 2 to n of 1 over k squared is actually just equal to the summation of k is equal to 1 to infinity of 1 over k squared minus 1. Okay, and that's just if you list out the terms of this in itself, you'll get 1 plus 1 over 4 plus 1 over 9, all the way down. So we just want to take this out, right, because we're starting from 2. So using this, right, we can then bring the 1 to the other side. Okay, so I'm gonna get rid of that. Right, we can then just take this 1 to the other side. Sorry. And then we get that as well. The summation of k is equal to 1 to infinity, 1 over k squared is less than 1 plus natural log 2. And that's it. That's the answer. That was it's quite a short question, right? Because I think 90% of the difficulty of the question literally just comes from realizing the substitution that you have to make. And yeah, sorry, I'm a bit ill, but yeah, realizing the substitution you have to make and then going through with it. But yeah, not a bad question, not too awful. But I can imagine in an exam condition, you're seeing that, you're kind of confused, and you probably are just more geared towards other questions. So let's look at the examiner report, because I think that's always worth doing with these types of like step questions, because it's nice to see what people found difficult, and then use that to your advantage if you ever see it in the paper or whatever. So yeah, let's see. Question 1. This is a popular question, but a number of common errors results in a relatively low average score for the attempts made. I wish they kind of put the average score, but that would. But I guess that doesn't matter. A number of candidates do not appreciate that it's necessary to check in the first part to check both that the gradient is positive and that x equals 0. Okay, yeah, this is important, because the reason what could happen is you can have like a curve like this, right? Which is technically increasing, right? This is an increasing curve, but it's not increasing from the origin. And because it's not increasing from the origin, right, you can't say that this function is positive for all values of x. So this is not sufficient. I don't know what it is. I think it's sufficient but not necessary, or it's the other way around. I forgot. If someone knows, put it in the comments. But essentially, yeah, even though it's increasing, it is not. It is necessary that it is increasing from the origin, which it needs to be stated. So yeah, fair enough. And additionally, many candidates failed to note that the next part of this question instructed them to use the results shown in the second section of part 1, and instead use the graphical method. Okay, that makes sense. Because honestly, if I was new to STEP and I was doing this question, I would probably try use a graphical result to try and show this, even though I have no idea how you would show a graphical result, because it literally makes no sense, because you just randomly got a variable called k. I would probably try that. But yeah, it's a step question. You're always going to need to do the part before, or use the part before for the part after. So yeah, and also just kind of use these numbers for hints, right? Like literally, this one kind of was the biggest hint for me, because you can't get a 1 in this equation unless you somehow have log to the base e. Sorry, not log to the base. Sorry, natural log to the e. Sorry, natural log e on the right hand side. But that just would never come out, because we don't. First of all, we don't know the formula. I don't think we're expected to know the formula for what e is, and yeah, so that 1 could only come from the left hand side. But yeah, no, good question. Also, apparently, incorrect use of the chain rule. That's just, I'm guessing, just a silly error. But yeah, not too bad of a question. But apparently, it seemed to be a bit tricky, which I can understand. This is it's a bit of a different one. It's not very long. It's actually a very short question, so you can really bag 20 marks on this very quickly. And yeah, thanks for watching. If you guys have any step questions you want me to go over, please put them in the comments. I would love to do it. I have a lot of time this summer. So yeah, thanks for watching.